In today's lesson, we are going to start talking about union probability, which some people you'll hear will call this is the addition rule for probability. Okay, and so this is going to combine two things that we have talked about so far. It's going to combine what we talked about with unions whenever you did Venn diagrams, and it's also going to talk about probability in general. And so we're putting these two things together. All right. So before we get started, I'm gonna remind you a little bit with probability, and one word that you will hear, or one, I guess, set of words, vocabulary that you will need to know is sample space. Okay, and you have actually been talking about sample space the whole time, but because they don't use these words a whole lot when it comes to probability, I wanted to review them. So sample space is just the set of all the possible outcomes. So if you're talking about an event or doing something in an experiment or whatever, and you're thinking about what is everything that could happen, what's all the possible outcomes, if you actually listed those out, that would be called your sample space. Okay. And if you remember, probability, to find the probability of something happening, you count how many times you could be successful. In other words, how many times could you get what you want to happen? And you take that and put it over the total number of outcomes, or the total amount of possible outcomes, which is if you counted how many things there would be in your sample space. All right. So just to kind of get your mind back on it, we're going to do a quick little probability problem, and then we will start talking about how does that relate to the unions that we have done with Venn diagrams, right? So the example says, what is the probability of getting an odd number when a die is rolled? All right, well, if we think about the sample space, and you can write it one of two ways, okay? One way to write it is as a set, so they'll put an S for the sample space, and then they'll put the little bracket for the set notation. So if we actually listed out what's everything that could happen when I roll a die, well, I could get a 1 or a 2 or a 3, a 4, a 5, or a 6. And so that is actually the sample space for when I roll a die. Okay. And so what we're wanting to happen here is it says we're finding the probability of getting an odd number. So a success in this problem would be if we get an odd number. And so that's actually kind of like a subset of our sample space. So think about what all of the numbers are that are odd. Well, that would be 1, 3, and 5. Okay. And so we're trying to find the probability of that happening. All right. So that's actually one way of thinking about the sample space. And another way is you can think of it as a Venn diagram. So remember, the universal set is all of the possible things that could happen. So that's kind of like your sample space. So this is like your sample space. And then if we're looking at a smaller set within that, that could be like your odd numbers. And so we would put all the odd numbers here, which were 1, 3, and 5. And then all of the other numbers that are not in this set would be outside of that. So like we could put 2, we got a 4, and we got a 6. And so that would be a way of representing this problem. All right. And so you can think of it like a Venn diagram. You can think of it like just writing out your outcomes, okay? And then that actually makes it easy to find your answer. So it says, find the probability of getting an odd number when a die is rolled. Well, how many odd numbers are there? Well, there are 3 out of how many total possibilities are there in all? Well, you can count here, 1, 2, 3, 4, 5, 6, or you can count in the Venn diagram how many there are in all, but there would be 6. And then you just reduce it. So that would reduce to 1 over 2. So there is a 1 out of 2 chance, or in other words, a 50% chance that I'll get an odd number when I roll a die. All right. So that's just probability in general. So what we're going to talk about now is how does this relate to the union stuff. All right. And so there is a question that you need to look for to know if it makes it a union problem. Okay. So if you're looking at a problem and it says something like this, what is the probability of this? So I can't really put anything in there because we're not actually doing a problem, but what is the probability of something happening or something else happening? That is a union problem. If you think back to when we did union with Venn diagram or Venn diagrams, we talked about union sometimes are called your or problems. And this is why. Is because if they say in a problem, what is the probability? So they have to ask it, what's the probability in there? But it says, what is the probability of this or this happening? That is a good indication that it's probably a union problem. Okay. Now, keep in mind that we do use the word or in everyday language. So just because a sentence has the word or in it does not guarantee it's a union. It has to say it kind of like this. What is the probability of this or that happening? Okay. And so just keep that in mind. All right. And then the notation will probably be a little familiar to you. So if you remember, probability is a P. So the probability of, and instead of just leaving blanks, I'll put letters. Let's say that they're saying, what's the probability of A happening, just to be general? Or remember, the symbol for union was this, almost looked like a U. So this is the probability of A or, and we'll put B happening. Okay. And so that's the notation to look for also to know it's a probability or a union probability problem. All right. So this directly translates to what is the probability of A or B happening. Okay, so if it's one of those questions, then you're going to more than likely be doing it as a union probability problem. Okay, and so when you figure out it is one of these types of problems, a union problem, then you actually have a decision to make. You have to decide, are those two events that are mentioned what's called mutually exclusive or not mutually exclusive? And so if it's mutually exclusive, which is also sometimes called disjoint, then what that means is those two events have no outcomes in common. And so one way to think about it in terms of probability, and so I'll put it down below it, is it means that these two things, they can't happen at the same time. At the same time. So kind of a very simple example of that would be, let's say that I come to an intersection and I think about the problem, which I wouldn't, you'll see why in a second, but I think about the problem. What is the probability that I'm going to go left or right? Well, when I'm driving, I can either go left or I can go right. I can't go both left and right. And so that would be an example of mutually exclusive events. The concept of left and the concept of right, they cannot happen at the same time. And so those would be mutually exclusive. Okay. Now, if you're thinking about it in terms of the Venn diagram, mutually exclusive events have nothing in common, no outcomes in common. So if you look at A and B, so you have all the possibilities that could happen with A, and then you have all the possibilities that could happen with B. If they have nothing in common, so that's another way of thinking about it, nothing in common, then that means that they would not overlap, because the only reason two things would overlap is if they do have something in common. Okay. And so mutually exclusive events in terms of like the Venn diagram would be the ones that do not have an overlapping part. Okay. So with that, you can think about it as in terms of like what they have in common. So that would be like their intersection. So remember, that's that upside down U, or like intersection. You can think of it like an N. Okay. But the intersection is what they have in common. So if they don't have anything in common, then the intersection would be empty. It would be that empty set, okay? And so if the two things cannot happen at the same time, then you would call them mutually exclusive. And the way that you work the problem would be a little different than if they did have something in common, okay? And so before we move to talk about how you would actually do the probability problem, we're going to talk about, well, if this is what mutually exclusive means, that they can't happen at the same time or they don't have anything in common, then think about what not mutually exclusive would mean. Well, that would be the opposite. And so the opposite of having nothing in common would be that they do have stuff in common, okay? And so not mutually exclusive, and I kind of think about the root word of exclusive or is like excludes. If you're not excluding somebody, then maybe you have something in common. I know that's kind of a weird way to think about it, but you got to think about it however you can remember it, okay? But if they're not mutually exclusive, then that means they do have outcomes in common, okay? So with this one, with probability, this means that they can happen at the same time. And you'll see why I keep saying it that way in a second. So they can happen at the same time. Okay, and so with this, if you think about the Venn diagram, these would be the ones where they would have something in common. And so the Venn diagram, they would have that overlapping part. Okay, and so you would have to consider that part where they overlap, where they have something in common. Okay, and so let's write that to the side. So they do have something in common. So they would have an intersection. Okay. And so these would be things that could happen at the same time. Like if I say I walk into a random classroom one day and I say, and I pick somebody out, and I'm looking at the probability that they like music and have brown hair. Well, there are people that like music and have brown hair. So those two things can happen at the same time. And so there's the people that like music, there's the people that have brown hair, and there's some people that will be both. And so that would be two events that are not mutually exclusive. Okay, and so before talking about the actual probability side, we're going to go down here and we're going to practice some problems about telling whether things are mutually exclusive or not. Okay, and so in number one, it says, are the following events, E and F, mutually exclusive or not mutually exclusive? All right, so in part A, it says a student is selected from school. One event is that they're a boy, and then the other one is that they have brown hair. So looking at these two things, can they happen at the same time? Like, so think about all the boys. Think about all the people that have brown hair. Is there going to be an overlapping section? Like if you drew a Venn diagram. So these are the boys. These are the people that have brown hair. Is there going to be some people that are both a boy and have brown hair? Well, yeah, there are boys that have brown hair. So because you do have some situations where they can happen at the same time, there are people that are in both of those categories, then you would say that these are not mutually exclusive. They are not excluding, I guess you can think, each other. Okay, so let's do the next one. Let's say that a coin is selected from a bag of coins. So the first event is that it's a dime, and the second event would be that coin's a quarter. If you reach into a bag and you pull out a coin, could it be both a dime and a quarter at the same time? Like, are there some dimes that are quarters? And no, it's either going to be a dime or a quarter. So this would be one where they can't happen at the same time. And so these would be mutually exclusive because they can't happen at the same time. And then the last one, it says a box of chocolates contains 6 milk chocolates and 4 dark chocolates. 2 of the milk chocolates and 3 of the dark chocolates have peanuts inside. You randomly select and eat a chocolate. So the event that the events that we're looking at is milk chocolate. So you pick out one, and you're looking at milk chocolate, and then if it contains peanuts. So can these 2 things happen at the same time or not? Are there milk chocolates in that bag or whatever they're in that have peanuts in them? And if you look, it says right here, 2 of the milk chocolates have peanuts. So because some of those have peanuts in them, these can happen at the same time. So think about which one that is. If they can happen at the same time, that means that they're not mutually exclusive. They're not, I guess, excluding each other, if you want to think about it that way. Okay, so that's just practicing telling if events are mutually exclusive or not. Okay, so now that you can tell which ones are mutually exclusive or not, now we can talk about what do you do to actually find the probability of these events happening. There's just one minor difference, and really you can think of it as one kind of equation, and with one of these you have to do something extra, all right? So if the 2 things are mutually exclusive, then to find the probability, what you have to do is add the probability of each event occurring. So if you're finding the probability of A or B happening, and it was mutually exclusive, meaning they didn't have anything in common, then all you have to do is find the probability of one event happening plus the probability that the other event happens. Okay? Oh, wow. Just lost my eraser there. All right. So let me organize that a little bit better. Probability of A plus the probability of the other one. That's it. All right. Now, that's if they do not have anything in common or they can't happen at the same time. If they do have something in common, you actually have to do something extra at the end, okay? So if they are, in other words, not mutually exclusive, then you still add the probability of each. However, after that, you then have to subtract where they overlap, because what would have happened is you would actually end up counting this overlapping part twice. Once when you do the probability of one, and then again when you do it in the other one. So you have to subtract it out one of those times, okay? And so you'll see what I mean when we do the examples. All right, so the way that translates into kind of notation is if it's still the same problem, probability of A or B happening, but the reason why you have to do it a little bit different is because now they have that overlapping part. So you'd calculate the probability of one of them happening plus the probability of the other event. But now you have to subtract the probability of them both happening, which is the intersection. So it's the probability of A and B happening, okay? So this is that overlapping part in the Venn diagram, all right? And it's the probability of A and B happening, okay? So let's actually get into some examples so that you can see this in action, all right? So I'm going to have to flip the page here. So example number 2, it says, what's the probability of rolling a 2 or a 5 if a die is rolled once, all right? So again, you can think of it like all the possibilities you have, okay, which we had listed out on the other page. So what kind of problem is this? Notice it says, what is the probability of rolling a 2 or a 5, okay? So rolling a 2 is one of your events, rolling a 5 is the other event. And they're saying what's the probability of this or that happening. So it is a union. So before you actually try to work the problem, you want to try to figure out, is it mutually exclusive or not? Okay, so when you roll a die one time, is there a chance for you to get a 2 and a 5 right when you roll it or when you roll it? And no, you're either going to get a 2 or a 5. And so these two things can't happen at the same time. So that means that these are mutually exclusive. So if you're finding the probability of this or this happening, and the way you write it is we're finding the probability of getting a 2 or a 5, then all you have to do is take one and add it, or take the probability of one and add it to the other one, okay? So what we're going to do is take the probability of getting a 2 and add it to the probability of getting a 5, all right? So think about, if I roll a die, what's the likelihood I'm going to get a 2? Well, there's 1 2 on the die out of the 6 sides, so I'd have a 1 out of 6 chance of getting a 2, plus, well, what's the probability of getting a 5? Well, there's 1 5 out of all 6 sides, so there's a 1 out of 6 chance of getting a 5. And then we just add them because they can't happen at the same time. We don't have to worry about subtracting anything. So then when you add, remember the denominators have to be the same, and then you just add the top. So 1 plus 1 is 2 over, and then you keep the denominator the way it is, and then you just reduce. So 2 over 6 ends up being 1/3. So I have a 1 out of 3 chance that if I roll a die, that I would get either a 2 or a 5. Okay? All right, the next one. It says, what is the probability of rolling an even number or a number less than 5 when a die is rolled? Okay? So this might be one where listing out the sample space might be helpful. So if I roll a die, I'm either going to get a 1, a 2, a 3, a 4, a 5, or a 6. All right. And so it's saying, what is the probability of rolling an even number? So that's one of my events. Or a number less than 5. So that's the other one. Okay. So before we get going with actually doing the probabilities, we have to figure out, again, like we did up here, is this mutually exclusive or not? So is getting an even number and getting a number that's less than 5, could those happen at the same time? Well, you can think of it as a Venn diagram if needed. So you've got all of your even numbers, and then you have all of the numbers less than 5. So think about that. So all of my even numbers would be 2, 4, and 6. So that would be what goes here. And then we need to think about what are the numbers less than 5. Well, that would be 1 through 4, right? So is there any event or any of those where they would fall into this region? And yes, 2 and 4 are both even and less than 5. So those two would fall in this little overlapping part here, okay, because those two can happen at the same time. And then if we wanted to kind of finish our Venn diagram, the other even number that we have is 6, and that's not falling into the overlapping category. And then the other numbers that are less than 5 would be 1 and 3. Okay, and so that's kind of representing our situation here. Okay, so if the question here is, are these mutually exclusive or not? Well, since they can happen at the same time, these two events are not mutually exclusive. So what that means is you're going to add the probabilities, but then you have to remember to subtract that part where they overlap. All right. So when we do this, we're going to be calculating the probability of getting an even number or a number that's less than 5. So I'll just put less than 5 here. And so if we use our notation, we're finding the probability of getting an even plus the probability of getting a number less than 5. And then we have to subtract the probability of getting both. So the probability of getting an even and a number less than 5. Okay. And so probability of getting an even number. Well, there's 3 out of the 6 that are even. So 3 out of 6 plus the probability of getting a number less than 5. There's 4 numbers less than 5 out of the 6. And then we have to subtract where they've overlapped. And the reason that is because notice when you did this probability, you counted those two numbers that were in the overlap. And when you did this one, notice you counted those two numbers again. So because you've counted them twice, you can't do that. You have to get rid of one of those times that you've counted them. So that's why you subtract it, all right? So you're finding the probability of both of them happening. Well, there's two numbers that are both out of the 6. So you have a 2 out of 6 chance of getting both an even number and a number less than 5, right? And so from there, just like before, you do the little calculation and then you simplify. So the denominators are all the same. So just combine the tops. So 3 plus 4 is 7, minus 2 is 5. So it'd be 5 out of 6. And then that doesn't reduce, so that is as far as we can go. All right. So with the next problem, it's just getting extra practice with these problems. And now, if you are not a person that's used to cards, I have attached a little cheat sheet for you to kind of be able to count or see how the cards lay out. Okay. And so if you need to pull this out to kind of see the video so that it makes sense, then you can do that. All right. But we're going to do some problems with cards because I feel like this is kind of a good way to explain this as well. So let's say a card is drawn from a standard deck of cards. All right. Part A says, what is the probability of the card being an ace or a queen? Okay. Well, it is one of these problems because it's saying what's the probability of this or this happening. Okay. So just like the other ones, you're going to think to yourself, can they happen at the same time or not? So if I pull out a card, is there a chance where it could be both an ace and a queen? Like, are there aces that are queens in a deck? Which is a really strange question. But no, okay? And so these two events are mutually exclusive. And so if we're trying to find the probability of this or that happening, of getting an ace or a queen, we just add them. So probability of getting an ace or a queen, we just take the probability of getting an ace and add it to the probability of getting a queen. All right. So again, you can pull out that cheat sheet or you can just kind of think through it. But the probability of getting an ace or getting an ace, well, there are 4 aces in the deck out of the total 52 cards. So there's a 4 out of 52 chance of getting an ace plus, well, how many queens are in the deck? Well, there's 4 queens out of the 52 cards. So I have a 4 out of 52 chance of getting a queen. And so from there, we just add them. So it'd be 8 out of 52. And then from there, we just reduce what we've got. So 8 out of 52 reduces to 2 over 13. So we have a 2 out of 13 chance of getting an ace or a queen. All right. The next one says, what is the probability of getting a 7 or a face card? All right. So again, and the face cards, because I want to make sure that we're clear, the face cards, I know it's pretty obvious, but the face cards are the ones that have faces on them. Okay. And so that would be your jack, your queen, and your kings. Okay. So it says, what is the probability of the card being a 7 or a face card? Well, can you pull a card out of a deck of cards and it be both a 7 and a face card? And that's another situation where, no, you can't have both a 7 and a face card if you just pick out one card. And so those are, again, mutually exclusive. And so you just have to add the probabilities of each. So probability of getting a 7 or a face card equals the probability of getting a 7 plus the probability of getting a face card. So the probability of getting a 7, think about how many 7s are in a deck. There would be 4 out of the 52 total cards, plus the probability of getting a face card. Well, your face cards, remember, are your jacks, your queens, and your kings. And there's 4 of each of those. So 4 plus 4 plus 4 is 12. So there's a 12 out of 52 chance of getting a face card. And then you just have to add them because remember, they didn't have anything in common or they can't happen at the same time. And so you don't have to worry about the subtracting part. So 4 plus 12 is 16. And that's out of 52. And so 16 out of 52 reduces to 4 over 13. So I have a 4 out of 13 chance of either getting a 7 or a face card. All right, the last problem in this set, it says, what is the probability of the card being a face card or a spade? All right, so it's again a union problem because it's saying what's the probability of this or this happening. Okay, so can they happen at the same time? So think of your face cards, think of your spades. And again, if you need to pull out this cheat sheet, you can. So you got your face cards, and then your spades. Your spade is a suit, and so this would actually be all your spades. Notice there are some face cards that are in that suit. And so this is a situation where they can happen at the same time. If I pull out a card, it could be a face card and a spade. So these are actually not mutually exclusive. So that means that I have to remember to do that little subtraction thing at the end. All right. So with this one, I'm going to calculate the probability of getting a face card. I'm going to add it to the probability of getting a spade. And then I'm going to subtract the probability of getting both. So the probability of getting a face card plus the probability of getting a spade minus the probability of getting both a face card and a spade. All right, so I'm just going to go down here. The probability of getting a face card, we actually figured out up here. It's 12 out of 52. The probability of getting a spade, so I add that to the probability of getting a spade. Well, spades are the suits. And so you can either count, but there's the ace through the 10, and then there's the jack, queen, and king. So there's actually 13 spades in the deck. There's 13 of each suit, if you want to think of it that way. And then we have to think about how many are both face cards and spades. So if I pull this back up, you can kind of easily see that. If you look at the spades right here, there's 1, 2, 3 that have a face on them. So there's 3 out of those 13 spades that are face cards. All right. So we have a 3 out of 52 chance of them being both. And then just like before, we just simplify. So 12 plus 13 minus 3 would be 22. And then that would be over 52. And then we reduce. So we have 11 out of 52 chance that it'd be either a face card or a spade that I pull out of the deck. All right, so the last problem that we're going to do together is a little bit different than the other ones, and this is why I want to do it, because you may see a problem like this, and you can still use what we talked about to do it. You'll actually notice that they actually make it a little easier on you, okay? So it says in this problem, in the cafeteria, the probability, or that's the same thing as percentage, of students that get chicken sandwiches is 0.6 or 60%. So there's a 60% chance that a random student walking in will get a chicken sandwich. And then it says of the students that get fries is 0.5. So the percentage of students, or the probability that a student walks in and gets fries, would be 50%. And then the probability of them getting both is 0.4 or 40%. Okay. So with this one, it says, what is the probability, I guess, essentially, that if a student walks in, that they would get a chicken sandwich or fries? Well, if you read this problem closely enough, it actually tells you whether these problems are mutually exclusive or not, okay? And it's right here. It says that this is the percentage or the probability of the students getting both. So because we know that some students will get both a chicken sandwich and fries, we know that there is an overlapping part. And so that means that because of this, these two things have something in common. So that means that they're not mutually exclusive. And so when we do this problem, just like all the other not mutually exclusive ones, you have to add the probability of each. So I'll shorten it. Probability of getting a chicken sandwich plus the probability of getting them fries, but then you have to subtract the probability that they would get both, okay? And so the reason why this one's a little easier is because we don't really have to do much calculating. They've done all the work for us. So the probability of a student getting a chicken sandwich, well, the percentage of students that got a chicken sandwich was 0.6, so that's what goes here. Plus the probability of the student getting fries, well, they told us 50% or 0.5 get fries. And then the percentage or the probability of a student getting both is 0.4. So we subtract the 0.4. And then we just figure that out. Or we just type it in our calculator and have our calculator give us the answer. But when we do that, we will get 0.7. So that means the probability of a random student walking in, getting a chicken sandwich or fries is, and that translates to 70%. So 70% of the students in this school will get either a chicken sandwich or fries. So there we go. Let me know if you have questions. Have a wonderful day.